Hello everyone. So in this video, we are going to see a transient-based question, and basically it is a capacitor-based circuit, and we will analyze how the capacitor behaves. And let's say you have these two capacitors, and these two capacitors have some initial energy, and these two are connected in series. So capacitor C1, the capacitance of the C1 is 3 microfarad, and capacitance of the capacitor 2 is 4 microfarad, and these are the respective initial voltages. And you are closing this switch at t equals to 0, and for t greater than equal to 0, the current is given as 80 to the power minus t microampere. You need to calculate what is the energy that will remain be there in capacitor C1 and C2 at steady state. Okay, so basically, if you want to know the energy stored in capacitor C1 and C2 at steady state, you need to calculate the voltage that will be there in capacitor C1 and C2 at steady state, because uh, the energy uh, stored in a capacitor at any given instant t is given by half C V of t whole square, right? And this particular energy is energy stored by capacitor at any given time t. Now you need to calculate at steady state. So basically you need to calculate the steady state energy. So E infinity half of C V of V infinity, right? So if I know this V infinity, then it will be easy for me to comment on the what is the energy stored in the two capacitors, okay, at a steady state, or energy remains in the capacitor C1 and C2. Okay. Now let's say if you have a capacitor, okay, and let's say this is your voltage across capacitor, and this is your current flowing through the capacitor, and capacitance of the capacitor is C, then the capacitor current is simply C dV by dt, right? So you all know this. So this equation is useful to calculate the voltage. Now here the direction of the current, you can see this direction of the current is simply leaving the positive terminal for both the capacitor. So if I want to write the operating equation of capacitor, I need to provide one minus sign. Let's say if I'm assuming the current is leaving, I need to provide one minus sign here, right? So same thing we will do here. So for C1 capacitor, so I of t is equals to minus C1 dV1 by dt. Voltage across capacitor, let's say I'm calling V1, okay? Capacitor C1, voltage across capacitor C1 is V1, okay? Now I of t is simply 8 e to the power minus t, and C1 is 3, okay? So I'm not showing this micro because micro and micro will be cancelled from both the end or both the side. So just I'm ignoring this minus 1. So it you will get 8 by 3 e to the power minus t dt is equals to dv1, okay? Now integrate it. dv1 is equals to 8 by 3 e to the power minus t dt. And let's say at t equal to 0, you initial voltage was 4 volt, right? So initial voltage was 4 volt, and at steady state you have the voltage V1 infinity, right? So this is your voltage at infinity. So if you solve this particular equation, so you will get 8 by 3 e to the power minus t by minus 1, 0 to infinity, V1 infinity minus 4 is equals to minus 8 by 3, 0 minus 1, V1 infinity is equals to 4 plus 8 by 3. So it will be 20 by 3 volts. Okay. So this will be the voltage that you will get. Maybe I can check the calculation one more time. 6.6623. Mm, is it correct? So initial voltage was 4 volt, and we need to calculate the current. Okay. Mm, 8 to the power minus t minus 3 microfarad, 8 by 3. Uh, yes, it is correct. Now we will do the same for the capacitor C2. Okay. So for capacitor C2, uh, I of t is equals to minus C2 dV2 by dt, minus 8 e to the power minus t. C2 is simply 4 microfarad, or dV2 by dt. Okay, actually here I missed one negative sign. So this negative sign I missed it. So yeah, so here negative sign will come, negative, negative. Okay, this negative negative will become positive. Yes, so that's why I was thinking why this voltage is becoming 20 by 3. This is more than that, the previous initial voltage. So it should be reduced. So 4 minus 8 by 3, it is 1.33. So mm, 4 by 3 volt. Now it is okay actually. So basically you can think like that way also. Like you got some calculation mistake. And basically, see this particular circuit, this capacitor, for both the capacitor is kind of delivering the energy, because the currents that is coming out from the capacitors are, you can see that it is leaving the positive terminal. So what will happen? Both the capacitor will simply deliver the energy, and if it is delivering energy at a steady state, this voltage, or you can say this voltage, both the voltage needs to reduce. Okay, and then only it will be able to deliver, right? So, and if it delivers the energy, the voltage should drop down. But what previously was happening, the voltage was increasing, which is absolutely wrong. So this is how you can think of. So even if you got some result, and you can basically, based on your intuition, you can comment on whether the value you are getting correct or not. Okay, so this will be the voltage at infinity at across capacitor C1. Now for capacitor C2, dV2 by dt minus 2, 0 to infinity e to the power minus t dt. Initial voltage was 6 volt. 2 v to infinity minus 6, right? So 6 minus 2 is v to infinity 4 volt. So this will be the voltage, and 4 by 3 is the another voltage. So for capacitor C1, for capacitor C1, C1 value was what? 3 microfarad and 4 microfarad, right? So okay, so 3 microfarad, and V1 infinity is 4 by 3 volt. For C2 is it was 4 microfarad, right? Yeah, 4 microfarad, and V2 infinity is 4 volt. Yeah, this will be the steady state voltage. Now you can calculate the energy also. So E1 will be half C1 V1 infinity whole square, half into 3 micro into 16 by 9, right? So 3 into 16 by 2 into 9, 2.66, so 7 microjoule. And E2 half into C2 into V2 infinity whole square, you will get zero point 0.5 into 4 into 4 square. You will get 32 joules. what is the initial energy? Initial energy was E1 E1 0 um, half into 3 into the initial voltage was 4 volt and 6 volt, right? 4 volt. So you'll get 3 into 16 into 0.5. You'll get 24 joules, and E2 0 half into was 4 into 6 square. It was 72 joules, microjoules basically. These all are in microjoules. This is also microjoule. You can now calculate what is the energy that got transferred into the external circuit. Okay, so either you can follow this method. It is the basic method. You can solve any kind of capacitor based circuit by using energy based questions if it is a first order or second order and all. So then equations and all will be a bit different, but this is how you have to approach to get a steady state energy and all. Okay, now there is one more way you can do this particular question. So what you can do, see this there was two capacitor present here, and this was some circuit. Okay, now you got some current here, and see this current is flowing through this capacitor C1 C2. So the current is simply dq by dt, right? Now if you calculate the charge that is getting transferred from this to this circuit, like this two capacitor into this particular circuit, I want to see what is the charge that is getting transferred from these two capacitors to into this particular external circuit. So for that we need to take help of integration, right? So dq I of t dt, and let's say mm, you want to do the integration, so I of t dt, and what is the initial charge was there? Let's say the initial charge was q naught, and at infinity the charge is uh, q of infinity dq. Okay, so at initially let's say t equal to 0, and I want to see the charge at infinity. So the current that was coming out, that was 8 e to the power minus t micro. Okay, because then it will be dt, it will be microcoulomb, right? So this change, this particular change I am calling delta q, because delta q basically simply q of infinity minus q of 0. Okay, this particular quantity I am calling it as delta q is equals to 8, what will be the value? 8 microcoulomb. Yeah, so this both the capacitor is basically transferring this amount of charge, and since these two capacitors are in series, so if this particular capacitor is delivering 8 coulomb of charge, this particular capacitor will also deliver the same amount of charge because both are in series. So if this capacitor is delivering 8 microcoulomb charge, this C1 C2 also needs to deliver this amount of charge. Now what was the initial charge stored in this capacitor C1? C is equals to Q by V, right? So you can calculate the initial charge. Q is equals to CV. So it was 12 microcoulomb. Initially it was 12 microcoulomb. And for this capacitor C2, 24 microcoulomb. Now you got deduction 8 microcoulomb from each. So it will be having C1 will be having the charge at steady state as 4 microcoulomb, and here it will be what, 16 microcoulomb, right? So C2. So this is how the circuit will look like at a steady state, this particular one. Now you can basically comment on the voltage that you will get at a steady state. Okay, so C1 was basically what? C1 was 3 microfarad and C2 was 4 microfarad. So 3 microfarad and C2 was 4 microfarad, right? So from this also you can calculate. So this is your Q1, this is your Q2 at a steady state. You can calculate the voltages. So V1 at infinity is simply Q by C. So 4 by 3, and here the V2 infinity is simply mm, Q by C, right? So 16 by 4, 4 volt. So this is basically much more easy in this particular case. So if you take help of the charge, like how to calculate the charge and what will happen, so then it will be much more easy rather than going into the conventional the operating equation of capacitor. See, this method is gives you the you can say the more understanding, like how the things are happening. Even it is more fast, because here the only thing you need to understand here is, for a series circuit, let's say you have n number of capacitor connected in a series. Let's say you have n number of capacitors connected in a series. Okay, and let's say for a specific time duration, the charge that is coming from this particular circuit is maybe some Q. Okay, so that Q needs to come out from all the capacitors, because all the capacitors are in series. So as you know, the current is simply I of t is equals to dq by dt. Okay, so you can see there is a kind of linear relationship I of t and q. So I of t kind of a linearly dependent on this q of t. Okay, so if there is any like mm, the nature of the current and nature of the charge will be almost same, you can say, because here you can see the for a series circuit, current is always same. So if the current is same, then my current the charge flow also needs to be same, right? So, so this particular you can apply this particular concept in this question. Like if this particular capacitor is delivering q amount of charge, so all the capacitor needs to deliver that q amount of charge only, or else, like you can say, the KCL will not work here. So to you have to verify the KCL, and so you have to satisfy the KCL and all. So then like this particular conclusion you can draw. But still, if you have any doubt regarding this discussion, you can ask me in the chat box. Thank you.